WhatsApp me such that I can just check the connections. So, as I said in the class, let us try to do some set of problems. Just the first trial that I just want to see today. And let me begin with the problem. So, the first two set of problem that I'm going to do is based on the diode connected configuration. So let me write down the problem. Also assume W by L of 1 is 50 by 0.5 and W by L of 2 is 10 by 0.5 and lambda and gamma are considered to be equal to 0. And the circuit that we are going to use is a diode connected structure with NMOS as the load or the diode connected device, and the input is again connected to one more NMOS structure, and I'm tapping the output across the drain of M1, which is V out. Right. So now for this, we need to figure out two things. One, at what input voltage is M1 is at the edge of saturation. And under this condition, we also need to find the small signal gain. So now the very first thing that we could able to note is that we are being asked to figure out what is the value of this input voltage of this M1. And also it says that we are at the edge of saturation. So obviously there is something that we have to relate ourselves for in order to identify this input voltage, we have to relate ourselves to the DC quantity. So having said that, we first need to find out what is the value of V out, or basically how to proceed this particular set of things. Okay. So now one thing that is given over here is that this M1 is at the edge of saturation. So now what it really means is that the value of V out is nothing but the value of drain to source of M1 transistor, and if this transistor is in edge of saturation, then it obvious that the VDS value of this is exactly equal to the VOV of this M1 transistor. So because of that, one could write the VDS1 to be equal to VOV1 or VGS1 minus VT. Now, and also what one could conclude is that the current that flows through this M1 and M2 would be the same. So I'm just going to use all of these factors in order to solve an equation. Okay. So basically the last factor that I said is that the currents of ID1 and ID2 are going to be equal, and I'm just going to assume that each of these transistors are in saturation. So I'm just going to substitute the corresponding saturation current equation, which is VGS1 minus VT the whole square, supposed to be equal to half Kn dash W by L of the second transistor or the diode connected transistor, VGS2 minus VT the whole square. Yeah. So now that we can just cancel out some of the common terms that we have, obviously half could be cancelled, Kn dash could be cancelled, and what is left over is just the product of W by L and the VOE values. So now that one could expand this value of VGS1 and VGS2 in terms of the known quantity, right? So what I'm going to do is that let me write this this VGS1 is nothing but is equal to Vn, and in the case of VGS2, the value of this VGS2 could be returned as something like Vg minus Vs, and we know that the gate potential is basically connected to the VDD, so one could substitute that value, and whereas at the bottom the source node is basically connected to the Vout, so I can again write this as Vout. Now one thing that we have to remember is that this Vout could be related back to our input voltage Vin through this expression, right? So now based on that, I could write this to be equal to VDD minus this VGS1 or Vin1 minus Vt. Hope that you are clear. So I've got both these sides VGS values expanded in terms of Vin alone, right? So now that I just rewrite this expression as W by L of 1, and in the place of VGS1 I'm going to substitute it as Vin minus Vd the whole square, and over the right side I have W by L of 2, and a lot of expression has to come in the place of VGS2, which is VDD minus Vn minus Vt, and yes, did I miss something? Yeah, so I basically have to have a positive sign here rather than a negative sign, so due to which I need to substitute a plus Vt, because when we try to expand this VGS2, the source is basically a negative value of Vout, and that when I try to plug in the place of this expression, then obviously we have to invert these expressions. So because of that, we have something like this, right? And apart from this entire expression taken as VGS2, we also have one more Vt that is sitting over there, which has to be added along with this expression. So now that you could able to see that we could able to further cancel out these Vt's that is coming out of VGS2 and the VOV2, right? Yeah. So obviously we are, I have to add an extra page. So okay. Yeah. Yeah. So now that the above expression could be further refined and re-return as something like Vn minus Vt whole square divided by W by L of 2 divided by W by L of 1, and this whole lot of expressions step down to a simple expression something like this. And now that I can just take a square root on both the sides in order to simplify this expression. And when we do so, since because we are dealing with the value with the NMOS transistors, the VOV of each of these transistors will be a positive quantity. So when I take a square root of this quantity, I could happily end up having just the positive value rather than holding plus or minus, right? So that is what I'm trying to use it here. And so this square root would end up having a positive value, and over the right I retain this Vn minus Vd. Okay, so now that we have done with it, now we have to do a simple algebra just by moving Vn to one end and the remaining terms to the other end. So I just try to move this Vn term that is available on the right towards the left, so that a 1 value would come from here, and there is a negative sign, so because of that the W by L factor would appear here, and I'm just going to move the Vt on the other side with the value of VDD. So suppose VDD multiplied with this factor W by L And then here there is a negative sign Vt. When I pass it on to the right side, it becomes a plus Vt. Yeah. So now I'm just going to plug in the values that were defined at the beginning. Okay, so basically the value of VDD was given as 3 volt, and the value of VTN, which is nothing but the NMOS transistors uh, threshold voltage, is basically 0.7. And we also try to remember this value, which is 1.34 into 10 to the power minus 4 amperes per volt square for the K dash. And I think this is not really required, but what is really required is this ratios W by L of 1 and W by L of 2. Okay, so one could even further rewrite this 50 by zero point 0.5 as something like 100, such that it makes our computation a bit easier, and this would be equal to 20. So with those in hand, what I do is that let us try to have this with, so I'm just directly substituting the values here. So I hope that you could able to follow this. Okay, so after trying to solve these values, you would end up having something like this. So in numerator we'll have 2.04, and the denominator will then have 1.447, and the total value would then be equal to something like this. Okay, so this is the input voltage that I need to have if at all, if this transistor is being biased, if my M1 transistor is being biased at the edge of saturation. Okay, so that is the whole concept that has been given. So now that we have computed the first calculation, where we are being asked to compute the input voltage, now the second part of this question is to identify the small signal gain at that particular region, right? So what I do is that, let me try to add up one more page here. Yeah, I'm just doing something wrong. Yeah. So now that we have done with this V in computation, now let us calculate the gain. Okay. Now for a diode connected configuration, we know that the gain is basically defined as GM1 by GM2. Okay, and we have already said an assumption to be followed. That is, the lambda is supposed to be considered as 0, and the gamma is considered as 0. Right. So because of that, we don't have any GMB effect here, or nor the R naught effect. Okay. So because of that, what we have is this. Now, in order to compute the gain, the easiest way that we can deal is that to replace this GM with three different forms of GMs, right? So one of the form would be K dash W by L and VOV. So this is number one. And the second form is 2ID by VOV. The third form is square root of 2ID K dash. Should we need to have W by L factor? I guess it's supposed to be K dash. I hope it's supposed to come, right? Yeah. So now one could really see that we cannot use this first form just because of the reasons that I said during the class, that there is no particular parameter that connects both the transistors. But what connects both these transistors is the current, because the current that flows through M1 and M2 are same, and due to which I can use either this equation or this equation for the purpose of computing this ratio for the gain. So now what I do is that I'll just, because we already know the value of WBL factor, I would prefer this particular third form of my GM in order to compute this gain. So I'll just use that. So when I do that, when I do so, I will end up having something like W by L of 1 divided by W by L of 2 as a ratio, and that leads to something like square root of 5 and a value of minus 2.236. Right. Now, so we'll just go for the second part of the question, which is what input voltage drives M1 into the triode region by 50 millivolt. Okay, so let me explain this. Before that, let me write what is the second part of the second question? Okay, so what is the small signal gain under this condition? Okay, so let us try to again see what has exactly been asked. So again, we have been asked to compute the value of the input voltage. So it's obvious that we have to still go for the DC conditions in order to compute that. But the other thing that we have to observe is that right now the M1 transistor is not at the edge of the triode region, but rather it has been pushed into the triode region by 50 millivolt. Okay, uh, what I really mean right now is that the current value of VDS under this condition is basically, if at all, if I'm at the edge of saturation, my VDS value would be equal to VOV of the transistor. But right now, this VDS value is being further lowered compared to the value of VOV by this quantity. Okay, because again, one could think about the hand sign just to ensure that in order to have our transistor into the linear region, our VDS value is supposed to be lower than the value of VOV, right? Yeah. So now let us try to fix this. So what's supposed to be my VDS value would be then return as VDS minus this 50 millivolt supposed to be equal to VOV. So this particular condition ensures that my transistor M1 enters into linear region. Okay, so I have lowered this value of VDS by 50 millivolt. Hope that it makes sense. So yeah, so now let us try to compute the value of V out so that we could try to identify what exactly has happened. Okay, so now in the previous case, the value of V out that we had computed was, I think, what was our V out expression? I think it was VDD minus, sorry, I think I just have to get back to the pages. Yeah, so we have got this V out defined as something like VDS1, and that is supposed to be equal to VGS1 minus VT, right? So let me reframe the same expression down here, or reframe this expression in a better way. That is, our V out is basically is nothing but my VDS1 value. Okay, and currently this value is lowered from the VOE value. So what I can do is that I can just move this particular minus 50 millivolt to the other side. I think I've done something wrong in this, right? Yeah. So basically, we'll forget about this expression because I think I've just have done some mistake in this. So let me go with this. Whatever we know. Okay. So the value of VDS is currently away from the value of VOV by 50 millivolt. Okay. So that would lead to something like 0.05 volt. And we supposed to know what was our VOE value for the previous condition when we had at the edge of saturation. So again, to compute this, one could use VOV is defined as VGS I think I'm just messing up with something else. So just give me a second. I just want to compute. I just wanted to know the value of V out. Yeah. Yeah. yeah, we have got this value of Vn, right? Yeah. So, uh, sorry for the interruptions. Like we have in the previous example, we found the value of VGS Q, and we are going to use that in order to calculate this VOE. Okay. Yeah. So we know that the value of VOE1 is basically defined as VGS1 minus VT. Okay. And the value of VGS1 or the Vn that we computed in the part A was turns around to be somewhere around 1.41, but I leave this 1 just for simplicity. Okay. So minus the threshold voltage, which is 0.7. Okay. So the current value of VOE1 for the transistor M1 was around 0.7 volt. Okay. Now, in order to push our transistor into the linear region, I have my VDS value has to be smaller than this value of 0.7, right? So I substitute here, and then when I do this simple math, we end up having this value of VDS1 to be equal to 0.65 volt as the current value of VDS1. Yeah. So now that my transistor are in linear region, that is my M1 is in linear region, but my M2 is in which region? So I guess you know that whenever we have a diode connected configuration, the transistor can operate only in two different regions, right? So one of the region would be cutoff, and the second region that we can have across this diode connected transistor is nothing but our saturation. So since there is already a current flow available across this M1 transistor, so we can consider this M2 to be in the saturation. Okay. So based on that, what I can do is that I can equate both these currents. That is, my ID1 is equal to ID2. Now, when I do so, we know that this current, that is my M1 transistor, right now has got into the linear region, due to which I have to replace this ID1 with a linear current equation, which is defined as Kn dash W by L of 1, and then Vn minus Vt, which is nothing but the VOE that we just now computed. Okay. And then into the value of VDS. So we know that the value of VDS is nothing but our V out itself. So I just write it as V out minus V out square by 2. Okay. And on the right side, where I'm trying to define the value of ID2, is nothing but the current that flows through my EM2 transistor, and we know that this transistor is in saturation regime. So due to which I substitute that current equation to be half Kn dash W by L of 2, and then VGS minus VT. Okay, so I'll just try to write it as VDD, where gate potential minus the source potential, which is nothing but our V out, and then the threshold voltage of the device. Okay, whole square. So now let us do some simple math. Okay, so you can just cancel out the common terms that are there. Okay, and so I think we have to do some pretty much algebra here. So I'll just try to do it, and you can parallelly try to simplify this expression, and let us see whether we are getting the same sort of expressions at the end. Okay, so I have something like Vn minus Vth1 or Vt, doesn't matter, and that's supposed to be equal to half W by L of 2, and then that is multiplied with VDD minus V out minus VDH whole square plus W by L of 1, and then V out square by 2, and this whole of this expression has to be divided by V out W by L of 1. Okay, yeah. So, and again, after doing all this math, you obviously end up having an expression of Vn, which is defined as something like half W by L of 2 divided by W by L of 1, and then VDD minus V out minus Vt the whole square divided by V out, and V out by half, or 2 into VD. Okay, so currently what I'm supposed to do is to substitute only these values in the place of these variables. So when I do so, I will just get some numbers which I just write down. And see that you're getting the same value at the end. So the first expression, or the first term, leads to a value of somewhere around 0.4188, and the second expression, or the term, gives me a value of 0.325 and 0.7. So when we add up all of these quantities, one would end up having something like 1.44 as the V in value. So obviously we know that it's a CS amplifier and it's an inverting amplifier. The way that I can reduce this value of V out is by increasing the value of V in, right? So when the V in rises, obviously the V out drops, and that drop in the value of V out is what we had as from 0.7 it has got dropped to 0.65. Okay, there is a difference of 50 millivolt, and in order to have this drop, we had changed our input from a previous value which was around 1.4. we have increased to a value of 1.44. Okay, yeah. So hope that you have understood. Now let us try to compute the value of gain again. Okay, so now the process of this computation of gain, I'm going to use the same expression of GM1 by GM2, and currently we know that this transistor M1 is right now not in the saturation regime, right? So due to which I cannot use the forms that I spelled earlier. So we have to again compute the value of this GM1 for a transistor that has been operated. Now we know that the definition of this GM in general is defined as a partial derivative of ID with respect to the VGS, okay, or the Q point of the VGS. So when I do so, now currently the value of ID that I have to substitute in the place of this ID is the saturation current equation. So which is again rewritten here. So V in minus VT, V out, and then V out square by 2. Okay, and then there is a partial derivative term with respect to VGS. Or I can even replace this VGS with V in, because we know that the value of VGS is equal to V in, so it's one of the same. Now the whole point is that we know that the value of V out currently that I have is basically 0.65 volt, which is lesser than the value of 1. Okay, now when I take a square of this in this case and then divide by 2, obviously this value would be somewhere closer to the value of 0.2 or something. Okay, so which is far less than the value of 1, and because of that we can actually drop just before we try to make a partial derivative on this entire expression. So hope that you are clear with this dropping of this term. We are going to neglect this term just because of the value of V out is less than the value of 1, and due to which one would end up having the value of GM1 in the linear region to be defined as something like K dash W by L into the V out. Okay, so this is the quantity that I have. So previously what we had was K dash W by L into VOV, and right now this VOV is being replaced with the value of VDS, right? Yeah. So we know all of these values, all of the factors here. So I can just go here and then substitute the quantities here. So I just write it as L of 2 VDD minus V out into VTH. Yeah. So hope that some of you might wonder, like, why did I use this? In the previous case, I said that I cannot use the form that has this VOV, and that is what I said. I cannot use this Kn dash W by L into VOV because VOV never connects both the transistor of M1 and M2. But what connects M1 and M2 is basically the ID, and due to which we actually neglected this particular quantity. But whereas here, you could able to see that the expression for GM1 and GM2, I have made use of this Kn dash W by L, and specifically for the bottom, I've used this VOE term. So how is this is possible? Now, one thing that we have to note is that I have a term that connects between this Kn dash definition and the bottom Kn dash definition. And what is that term? It's basically the V out. Okay, so there is a kind of term that connects both these expressions, and due to which I can use it here. Okay, so that's the reason why we have made use of this. And now let me try to get down to this. I can actually cancel out the common terms that I have here, and that would left over with the WL ratios. So I just use the values here. So it would be like 50 by 10, and V out, we know it is 0.65 divided by 3 minus 0.65 minus 0.7. Okay, so when we do all this math, we would end up having somewhere around 1.96. Okay, so that is the gain of this particular circuit when one of the transistor has got entered into the linear regime, okay, by 50 millivolt. So hope that this entire problem set was clear to you. And now that I'm just going to move for the second problem, which is again a diode connected, but we will try to solve with a different perspective. So right now the transistor the transistor M2 is being replaced from NMOS transistor to a PMOS transistor, and it has these following parameters being defined for it. Okay, so basically Kn dash is defined as 160 microamperes per volt square, and the threshold voltage of the NMOS transistor is basically 0.4. Okay, so this is my Vt, and again the Kp dash is equal to 36 microamperes per volt square, and whereas the threshold voltage of the PMOS device is different from the threshold voltage of the NMOS device, which is taken as Vtp is equal to minus 0.5 volt. Okay. Now also what is given extra is that the aspect ratio of our M2 transistor, which is 2 by 2, or is just the 1. Okay, and the supply voltage is given as 5 volt, and for the entire computation we can assume that the gamma value is considered to be equal to 0. Okay, now, and what else is given is that the gain of the circuit is defined as 5 when the Vout is biased at a value of 2.5. Okay, so we are going to use these two quantities in order to solve the part A and part B of this particular question. Okay, yeah. So now let us try to solve this. So the very first question that is being asked is to compute the width of M1 transistor, provided if the minimum length of L1, or the minimum length of my M1 transistor, is having 2 micrometer as its minimum length. Okay, and since because there is nothing specific about the lambda that is being given, I'm also going to assume that the lambdas for both these transistors to solve in this case of part A and part B to be equal to 0. Okay, so please make a note of that. Now, how do we find the width of this particular structure? Now, one thing that we can do is that the current value of this M2 can be easily computed just because we know the aspect ratio, we know the Kp dash value, we know the threshold voltage of it, along with the value of this source potential, which is right now at 5 volt. But what is unknown in this case is the gate potential. Okay, but one could really see that this gate is actually connected to our drain, or shorted basically, and that drain is basically connected to the Vout. And in the question we have already said that the value of this V out, in order to get a gain of 5, it has to have a value of 2.5 volt. Okay, so we are going to make use of that in order to derive the value of VGS2, and once we derive the value of VGS2, then we can use it to compute the current through M2, and from there we can make use of the gain expression in order to link ourselves to the W by L factor of this M1 transistor. Okay, so let us do one by one. So let me first try to compute the ID2 current, or the current that flows through this M2 transistor. So which we know that since there is a current flow, a diode connected transistor will be operated only in the saturation regime. So I can use the saturation current equation, W by L and then VGS2 minus VT the whole square. Okay, now a better way to deal with this PMOS is to always put the modulus across them, such that we will not get confused while substituting the values. Okay, yeah. So now that I just want to calculate the value of VGS2, which one could write it as something like VG2 minus VS2, and we know the voltage that I have across the source terminal of this M2 transistor is basically a 5 volt, so I can use that, and the voltage across the gate, which is nothing but currently the value of that is given as 2.5, so I can use that, and this would end up having a negative value here. Okay, so when I put a modulus, this becomes like 2.5 minus, again, modulus across this threshold voltage of the PMOS device. So when I do so, I can just make use of this value as 0.5 directly, and I have all these values, which is basically 36 micro, into the W by L factor, which is basically 1 over here. Just multiply each of these values. I guess you would end up having a value of 72 micro amperes as the ID value. Okay, so once you have computed this, then the next task is to make use of the gain value. So again, we know that the gain of the circuit is nothing but GM1 by GM2 for the case where the lambda and the gamma is assumed to be equal to 0, right? So again, and that value is set to be around 5, and we know that's an inverting amplifier, and we need a negative value of 5. Okay, so since do not get confused, so we will just put a modulus such that the negative value is not being taken into account. So what I have really is this particular expression, and now that we have to use some sort of GM such that we could able to connect to the W by L factor of this M1 transistor, which is what has been asked over here, right? So again, as I stated before, if I go for 2ID by VOV form, I might not able to get the value of this W by L factor, okay, for the place of GM. Now what I'm going to do is that rather of choosing this as my GM expression, I would choose the square root expression in order to compute my W by L factor, where already we know that a W by L factor is fitting inside this GM expression. So based on that, let us try to express this GM1 and GM2 in terms of the square root equation. So I have this 2ID k dash W by L of 1 divided by square root of 2ID kp dash W by L of 2, and that's supposed to be equal to a value of 5. Okay, so now again one could do a simple square relation, like taking square on both the sides. We would end up having 25 here, and then we could also do some simplifications here just by cancelling out these two terms, and what is left over is just the kn dash W by L of 1 divided by kp dash W by L of 2, and that's supposed to be equal to 25. Okay, so I think from here on it's just the ratios. If we do so, we will get a factor for W by L of 1 to be equal to 5.625. Okay, and we have to look back to our question, which was stating that we need to compute the width of the circuit, and where the value of length is given as 2 microns. So because of that, I would end up having a width for this M1 transistor to be 2 micron into this ratio or the factor, which would end up having 11.25 micrometer as the width of the input device. Yeah. So hope that we have solved the first expression. So now that we will try to solve the second problem or the second question. So we need to find the range of input voltage over which the MOS transistors are operated in the saturation regime. Okay, so we know from the definition. So I'll be using this figure in order to ensure that you understand what has been asked. So first of all, I need to define the base value of this V out, right? So the base value is nothing but the Q point. And we know that this Q point is supposed to be equal to VDD minus this VGS2. Okay. Now, whenever there is a swing across the input, okay, so I will use even the bias circuit here. Okay. So whenever there is a swing, this swing in turn creates a kind of swing around this Q point at the output, right? So a swing across my input Q point would create a swing across my output Q point at the output. So now how far this V out can go up such that my transistor stays inside the saturation regime. And from the theory, we got to know that this value is supposed to be equal to, that is my VO max supposed to be equal to VDD minus the threshold voltage of this particular device, which is nothing but my VTH. Okay. Oh, so let's try to give some room here. And since because we are dealing with the PMOS transistor, I generally try to put a modulus such that we are not getting confused with this with the values here. Okay. Now, similarly, what is the minimum drain to source potential that I need to have whenever there is a negative swing at the output? So, and that's supposed to be a value that is equal to my VOE1. Okay, so this defines my VO minimum value. So if you could able to find these two values, then our job is done. So let us try to figure out both these values. Okay. So the B question, my VO max was defined as VDD minus the threshold voltage of the device, of the PMOS device, and VDD was given as 3 and the VTP value is given as 0.5. So that leads to 2.5 volt as my VO max. So now let us try to evaluate the value of VO minimum, which is supposed to be equal to my VOE1. So how would we find this? So one could make use of the current that we evaluated at the beginning. Even though we never used it, one could make use of this current equation because the current has to flow across both the device. So now one could evaluate the value of VOE based on the expression that we have got, right? So since our transistor M1 is in saturation regime, I know that the value of ID1 or the value of this ID2 is basically equal to ID1, and I can use this current equation, which is W by L of 1 into VOV1 the whole square. Okay, so this is the quantity that we basically need to identify. So just do a simple algebra, you would get the answer for it. So I think the current value that we have for ID2 was computed as 72 microamperes. So I'm going to use that, and our VOE1 squared value would then turns around to be 160 millivolt, or not exactly millivolt because I have a square term, so it is basically 10 to the power minus 3. And when I take a square root of it, I have to take a positive value here just because I'm working with the NMOS device for computing the value of VOE1, and that always has a positive value of VOE. Okay, so because of that, I would end up having a 400 millivolt for the value of VOE1. So now that we have computed my VO max and my VO minimum, okay, so that's done. The third question that has been asked was, I guess what was asked is not the output voltage range, it is the input voltage range is being asked, right? So now again, so how will I compute that? So we know that uh, whenever there is an input swing, the minimum value that I can have across this input swing has to ensure that this transistor is never turned off, right? So the minimum value that I have to maintain across this value of VGS is supposed to be equal to VTH. Okay, so I could get that my V in minimum is basically my VTH value. But how to compute this V in maximum? So again, whenever there is a positive swing, what is happening is my gate potential is raised up, and due to which the drain potential is stepping down. Now there is a particular point where I have I could able to relate my VGS value with respect to my VDS value at the edge of saturation. Okay, so hope I have already explained all of these concepts with the animation for a CMOS amplifier with a resistive load. So I will not explain much, but the point is that I could relate this V in max with respect to VO minimum value through a threshold voltage. Okay, so I'm going to make use of that in order to compute it. So I have this V in max, which is nothing but the VGS minus VTH, supposed to be equal to my VO minimum. Okay, and the value of the VO minimum is basically nothing but my VOV1 that we computed here. Okay, and I just translate this VTH over to the right side in order to compute my V in max. Okay, so the summation of VOV1, which is 0.4, and the threshold voltage of the NMOS device is basically 0.4. That leads to a value of 0.8. So my V in max is basically 0.8, whereas my V in minimum is just equal to my VTH value, which is equal to 0.4. Okay, hope it is clear. So now that we'll just move on to the B part of this question, which is the C part of the question, which is being asked to compute the voltage gain and the output resistance for the small signal voltage, for the small signals at Vout equals to 1.26, and also they had asked to compute, they had asked to use this lambda n and lambda p in order to compute the gain. Okay, so there's a specific reason why this lambda values make sense. So what I do is that I'll try to begin without using this lambda values and then try to compute the value of gain. Okay, and then later I will just explain why this lambda values has to be included in order to account for this V out that I have. Okay, now this is the C part, so let me use a different color. Let me choose this. Now whenever I consider that my lambda is not equal to 0, so when the lambda is equal to 0 and the gamma is equal to 0, then the gain expression of this diode connected configuration would end up having as a ratio of GM1 by GM2, right? So in this case, if I try to expand, I could end up having something like what we have done before, the same old story. So again 2ID, I think Kp dash W by L of 2. Okay, so again one could cancel those common terms, and what obviously happens is that we end up having the same value of gain which was used in order to compute the value of W by L factor. Okay, so there is no change in this gain, right? Just because these GMs never took into account or cannot take the account of V out currently the circuit is operated in. Are you getting? Can you able to follow? Hope that you could be able to follow it. So the only way that I can encounter the present value of V out into this gain expression is by including the R naught impact. Okay, so the moment I consider that the lambda is not equal to 0, then my entire gain expression would then get modified as gm1 into rout, right? So where the rout value would be equal to gm2. I think I have this. Yeah. So when I look down, the impedance was just Ro1, and when I look up, it is 1 by Gm in parallel with R0 2. Okay, so that is the upward impedance, and when I look down, it is the Ro1 that I have. Okay, now is this gain equation encounters or pulls in the value of this V out into account? That is the question right now that we have. So let us try to answer that. Now, basically, in order to compute any of these GMs or R out, or basically R naught, we have to work with our current. Okay, so right now this current could be written as gain dash W by L for the bottom transistor into VGS minus VT the whole square. Now, when I include this as my current, obviously even this current couldn't be able to relate to the V out. But one thing that we can do is that since the value of lambda is given, one could also encounter the channel length modulation impact by having this extra term added to it. Okay, so whenever we had this lambda that is equal to 0, we never had this extra term. Okay, so but currently when the lambda value is given, then through the lambda I could relate to my V out expression or the present value of V out that we have. So which was given as I guess it was, what was the value? Let me just look back into this. So yeah, so previously we had a V out equals to 2.5 and we used that to compute the W bell factor, but currently the V out is right now stepped down by almost half the value of the previous value, and we will set that currently to be equal to 1.26 volt. Okay, now to take this into account, the only way that I can have here is to make use of this current equation with the lambda factor associated with it. Okay, so that's the reason why I said at the beginning that whenever we want to work with different values of V out to compute the gain, then somehow the lambda factor has to be included into our structure. Okay, structure of the gain equation. And the way that I can do is by first working with the drain current and then later use this drain current into the R naught through the lambda gain, and we could do everything from there such that it encounters the V out impact. Okay, so having done that, sorry for the disturbance, I'm just getting a call. Yeah, so we'll just continue this. Yeah, so yeah, so now what I do is that I'll just try to make use of those V out expressions and then try to compute this current. Okay, so we know that this value that I have, when I substitute all the values that I know. Yeah. So one thing that we have to ask is that can I currently make use of this equation to compute the value of ID? I guess I might not do so just because I have to encounter this V out, right? Yeah. So rather than working with this bottom transistor where I cannot encounter this V out expression, what I do is that I'll just try to work with the ID2 where I can write this ID2 expression as K half Kp dash W by L of 2 into VGS value, and again this VGS could be derived right away from the structure, which is defined as VDD minus this Vout minus VTP the whole square into 1 plus lambda into, again, the VDS of this would follow the same thing like VDD minus Vout. Okay, so I'm just trying to include all the possible ways I can include this Vout into account. Okay, so after doing pretty much all the algebra of substituting these values, I think VDD was 3 and the current value of Vout is 1.26. So was it 3? I think the present value, yeah, the VDD was 5 volt. Yeah, so the VDD value was 5 volt, so I would be using that. Okay, so 5 minus 1.26 would end up having something to a value which is 3.74, and the VTP value is basically 0.5. So again, I have to substitute the modulus here. Okay, so hope that you do so, and it's been squared with 1 plus the value of lambda p was 0.022, and so I make use of that 0.022 into the same value, which is 3.74. Okay, so when I try to solve this, I would end up having something, a value that is closer to 192 microamperes for this ID2. Okay, yeah. So now once I've got this value, I can make use of this current equation in order to compute the RO1 and RO2, which is defined as lambda n times that of ID. And after doing all the substitution, the value would be equal to 192.9 kilo ohm for RO1, and the value of RO2 would be lambda p into ID. So this value goes around 236.7 kilo ohm. Okay, and again, to fulfill this computation, I also need to compute the value of GM1 and GM2 for the current that I derived. Okay, so still we are yet to perform this computation. So which is 2ID by VOV2, and we have already computed the VOV value here. So just 3.74 minus 0.5 would give us something like 3.14 at the bottom, 2 into 192 microampere. So that gives us 122.3 microsiemens for GM2. Now I'll also use this GM1 with the square root relation, just because I'm not aware of the value of this Vn currently that I have. Okay. So yeah, so over here I still make use of my ID that I've computed earlier, and when I do this, so Kn dash is 160 micro into the value that we found for the ratio, which is 5.625. So this entire square root would end up giving us a result of 587.87 microsiemens for the value of GM1. Okay, now we end up having a very large expression computation for this. So yeah, so it is basically the ROut is nothing but GM2 parallel with RO1 parallel with RO2. So it's a lot of computation that has to be done. Okay, it's just a substitution and then do the basic math. So when you do so, this value would then get closer to a value of 7.6 kilo ohm. Okay, so substituting each of these quantities over here, we would end up having a value which is closer to this. And now I just want to compute the value of the gain, which is a product of minus GM1 into ROut. And when we do so, this turns out to be 4.46 volt per volt as the gain. Okay, so hope that everyone is clear with this, and let me try to stop my or end my stream here. So thanks for the people who are on live. Thank you.